Hello everyone. Today we discuss contest 24. Pretty hard contest, especially the last problem. I spent a lot of time solving the last problem. I'm surprised you solved it in just like 20 and something, 25 minutes. Very impressive, very impressive. Okay, maybe I overcomplicated things, so we will see. So we will, again, I pre-recorded myself, so we'll just watch how I solved all these problems. So first few problems are really simple. So in the first problem, you just need to check that it's possible to get sum of sum n minus 1. So you take all numbers except 1, and you need to check it's possible to take all numbers except 1 in such a way that sum is less or equal to s. It kind of makes sense to take all numbers except the largest one. So what I'm doing here, I sort all numbers because I can. Not very optimal, but why not? So I sort all the numbers and take sum of all numbers except the last one. So last one will be the largest. So I take sum of all numbers except the largest and check it is less or equal than s. That's it. Sorry. Like this. It's much better. So very straightforward, nothing interesting in the first problem actually. It's just the first problem to start the contest. Second problem is it's also very simple. So again, problem itself is not that bad, but the constraint of all numbers be less or equal than 10 kind of suggests you can make any time complexity solution and it will pass in the given time limit. So what I'm doing is just simply trying to, so I create a map R by C and put booleans in this map, and then I check all possible rectangles and calculate sum in this rectangle, check if sum is at least k. I'm doing it like this, so I like here I'll just make 4 loops. So I make left, right, top and bottom border of my rectangle just in these 4 loops. And then inside these 4 loops, I make another 2 loops, just counting number of elements inside this rectangle. So I have 6 loops in total. Time complexity n power 6. It's definitely not the best time complexity for this problem. You can solve it in much more efficient way, but you don't need to. If all numbers are up to 10, you can solve it like this, and it will still pass all the tests in a given time limit. Again, programming competitions are not about writing the most optimal code. Sometimes you write not the best code possible. You need to write code that passes the given test in a given time limit. That's it. So if constraints are small and you see that the less efficient solution will pass, you go for it. Yeah. Question. Can you please explain the problem with QSB? Which one? Second one. Yeah. Second problem. So you given it. Let me draw a picture for you. Sorry, I thought you read all the problems and kind of understand what's going on, but I'll explain solution. So statement of problem is very simple. So let me go back. Open problem B. Yeah. So problem statement is like this. So you have a table dimensions R by C divided into squares. And some of these squares contain some values. And you want to find number of rectangles that contain at least k elements. Yeah. So this number k is so I want to take a rectangle that contains at least k elements. And we'll kind of count number of rectangles like this. Okay. So this is the problem. And what I'm doing, I'm just iterating for all possible rectangles. For each rectangle, count number of elements and check if it is at least k. That's it. Okay, maybe problem statement is overcomplicated because of this. You have too many values. You have 4 values here. So, but problem itself is very easy. Again, you can make much faster solution actually for this problem. So my solution has time complexity n power 6. It's too much. You can make much faster solution, but you don't need to. Problem C. In problem C, what we have, we need to, so we have hamsters, we need to put them in boxes, and we know the capacity of each type of box, and we need to choose which type of, so we choose one type of the box and put hamsters in these boxes. And we want to maximize number of hamsters we can put. Again, let me draw some picture for you. So basically what we have n elements. So let's say array of size n. So n elements. And I have some type here. I have AI as a type. So I make box of some type. Yeah. So if I choose some type, some AI. Yeah. So if I choose the size of the box, I put some hamsters in some boxes, and some hamsters will be there. So this residue will not be used. Yeah. And the question is to pick the type so you maximize number of used hamsters. So instead, in what I will do, I will minimize number of these residual hamsters here. So this number is the number of hamsters left, so you cannot put them in a box, is just a remainder of division. So it's just n remainder of division by AI. And this thing I will try to minimize. So that's the whole idea. So I will just do it brute force. So I will check all possible sizes. For each size, I will calculate this remainder and pick the minimal one. That's it. Again, pretty overcomplicated problem statement, but once you understand what's going on in this problem statement, the algorithm itself is very simple. Check my solution. Okay, we'll check the solution. I thought, what's your handle? Okay, we'll check your solution. Okay. Yeah. Yeah, so what I'm doing here, I take the number, I calculate the remainder, here t is remainder, and just pick the minimal one. Okay, here I made few mistakes in this code because I'm not very careful today. Yes, first of all, I forgot you have big numbers here, so you need to use 64-bit integers. I'm not sure why I'm still not using 64-bit integers everywhere. Yeah, it kind of makes sense nowadays to use 64 bits just everywhere. I just don't like changes, I believe. So that's why it actually makes much more sense to use 64 bits just everywhere, not only when you actually need, but yeah. Also, yes, my second mistake is sometimes if none of these boxes fit, so your remainder is always n. So if all these values are greater than n, remainder is always n. So I don't change this value, so I output -1. So that's it. That's my solution for problem C. Let's check your solution now. This 5. Let's check. Makes sense. Okay. Now we iterate all boxes. Check if smallest is. Wow, you don't need for smallest box. Here you find the smallest box. That's not what you need. You need the minimize the remainder. This thing. So you minimize just the wrong thing. It's not the same thing. For example, let's say if you have, I don't know, if you have, so if let's say n equals, I don't know, 16, and you have two types, like you have 3 and 4. Yeah. So if you choose 3, so you pick 5 boxes of size 3, and the total size will be 15. Yeah. If you choose 4, you can make 4 boxes of size 4, and total will be 16. So 4 actually is better in this case. Yeah. So you just optimize the wrong thing in this solution. You see. Okay. Okay, so let's go to the next problem. Okay, so that's all you solved. Yes, so only one and okay. Okay. Let's move next. Oh, problem D. Sorry, problem D is strange. So, in problem D, you have okay. Let me draw you some pictures. So you have some basically periodic sequences with given periods. Yeah. So you have some guirlands and you put them with given steps. Let's say you put one guirland with step, I don't know, 2. So you put it here, 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 here. And then you have second guirland with step, I don't know, 3. So you put it here, and then with step 3, then step 3, then step 3. Yeah. And then the fourth guirland, so you put it somewhere else. Question is, is it possible to fill all the points with given periodic sequences? So you have 3 periodic sequences with given periods. So you have K1, K2, K3 given periods. And you need to check if it is possible to fill all the elements with given periodic sequences. No. Right now, when I think about this problem, it's okay. It's maybe much easier than I solved it. So, but again, you'll see my solution. So I think you can solve it like this. So let's sort all the numbers. So I have K1 less equal K2 less equal K3. So I have three sequences. So if they all are greater than 3, then it's definitely impossible. Yeah, because every sequence cover less than 1/3 of all elements. Yeah. So if all elements are greater than 3, let's see. So if all elements are greater, then they're definitely impossible. Then we just need to track cases when you have 1, 2, or 3. So if you have 1 something, you definitely can. Yes. If you have 2 something, then okay, you have now you have some cases. You have 2 and 2, you have yes. If you have 2, 3 and 3 is no. So 2 and then 3. Then I have this empty and this empty. I can cover them both. Yeah. Okay. So 2, 4, and 4 is yes. Yes. And that's it. That's all about 1, 2. And then you have 3, 3, 3. Yeah. I believe that's all cases when I have yes. All other cases will be no. Probably. But again, I wasn't sure about this. So maybe yes, maybe I missed some case. So what I did instead? So instead, I just make brute force. So I will just brute force all possible ways. So what I see again, important observation is if I have big numbers. So if these periods are big, it's always impossible. Yeah. So these periodic sequences with big periods will not affect the solution actually. So it only interesting elements are small elements. Yeah. And for small elements, you can just brute force the starting position. So for every sequence, I will brute force the starting position of the sequence. You'll see. And I know the starting positions are always small. So what I'm doing here? Okay. Oh, yeah. So here, so I have this. So this array K is this array of periods. This array A is array of starting positions, and I will brute force all 3 elements from 0 to max. Max I will set to 5, because why not? I'm pretty sure 5 should be enough. Yeah. But because of this reasoning, I know that maximum interesting element is 4. Yeah. So maximum equal 4 should also work actually. Even 3 should work. Yeah. But I will set 5 because why not? Yeah. So if I set it to 5, it will not be. It will not hurt. Yeah. So by setting it to 5, I will check more elements. But again, if it's possible, I will still find element. If it's impossible, then all elements will be impossible. Then it doesn't matter. Yeah. So sometimes I over check some things just to be sure. Yeah. because I see that I will have enough time complexity. So again, time complexity is small, 5 or 3, doesn't matter actually. Yeah. Okay, and here I'm checking 20 elements. I'm pretty sure if I check first 20 elements, they're all covered, then everything else will also be covered. So I iterate all combinations of this up to 5 and check 20 elements. Why 20? I don't know why 20. I believe checking like 10 elements will also work. Maybe even 5 elements will work. Yeah. But I check 20 because I can. Yeah. Again, I just set up this. Sometimes I just put this constant just from my intuition. If they didn't work, I would change them. Yeah. So if they didn't work a second time, I would probably think a lot. Yeah. So what I'm doing wrong? Maybe my intuition is wrong. Yeah. It happens sometimes, but usually you just pick it big enough. So you again. Sometimes you want to be careful because time constraint is small. So if time limit is small in the problem, and you feel like your problem is already too slow, then you put this constant very carefully. But here I see that time complexity is really small, so I have just 3 loops, each to 5. So it's like milliseconds. It's not even seconds. Yeah, you see, maybe nanoseconds. I don't know. It's very fast. Yeah. I don't care that much about this console. I can put here instead of 5, I can put like 50. It will still work. So I have 3 loops of say 50. Yeah, 100 input. Yeah, it will not it will not affect the uh, speed of this program that much. So it will affect, but it will still fit into time limit. Okay? So that's it. So that's problem D. Let's go to problem E. Okay. Problem E is interesting actually. In problem E, so I solve this problem not how I usually would solve this problem. So in problem E, you need to create data structure which allows you to do the given operations. So you have 3 operations, and you need to make a data structure which allows you to perform these 3 operations. And if you look closely, okay, so what are these operations? Let me think. Operations are like this. You have sequence. You have sequence of elements. You have following operations. First operation, take some prefix of this sequence and make plus x to all these elements. So it's the first operation. Yeah. So take some first a elements. No, okay, from 0, let's say, to a minus 1, and make like plus 6 to all of them. Second operation is just to add new element equal k to the end of the sequence. And the last operation is just to remove the last element. Okay? So basically stack where I can also increment some prefix of this stack. And if you think about it, you can do all these operations using segment tree. Yeah. So you just create a segment tree, just large enough. Yeah. And just use this prefix. And what you need to do, you need to calculate the average of elements. Average is basically the same as the sum of elements. So it's just sum divided by number. Yeah. Now I can maintain number of elements. So I basically worried about sum of elements. So I need to maintain the sum of all elements in my sequence. Yeah. So you can actually do it using segment trees easily. Yeah. You have a segment tree big enough again, and you just use this prefix as your sequence. So your sequence is here. Yeah? Then what you have operations? You have operation plus x to some segment. You can do it in segment tree. Yeah. You need operation insert element. So you need operation equal k. So you assign value k to this element. You can do it using segment tree. And you need to calculate the sum of all elements. No, you can do it using segment tree. So you can create segment tree with all these 3 operations. And in normal context, that's what I will do. So I will just take my default segment tree from my template and put it here and solve problem like this. So, and do we have time to try it like right now? I'm not sure if I have my segment tree nearby. Let's try to do it now, actually. So just to show you that it's that easy. Okay, maybe some of you did this. That's strange. Do you have segment tree? No. Oh, you have panic tree. Oh yes, so okay, that's it. So again, if you have like data structure like this, okay, you have panic tree here. That doesn't matter. So you can just use it in this operation, and that's it. Yeah. And that's much more preferable way to solve problems like this. So if you can solve problem using like default data structures that you already have on hand, just do it. Yeah, that's again, you have 1.5 seconds. Okay, for 2.5. So it should be good enough to solve it in time complexity like n log n. Yeah. So if you can do all these operations in log n time, it will definitely fit into 1.5 seconds. So you actually don't need to invent bicycles in this problem. Yeah. So that's my normal segment tree. Yeah. What it allows you to do, it allows you to do two types of operations. So one, modification. So you have like modify, and you have calculate. So what you need to calculate? You need to calculate the difference. Yeah. Difference. So I'll have item. So you need to calculate sum. Yeah. So my item will be just value. Long. And no item will be just 0. Now modification will be plus. Yeah. So let's click like this. Boop, 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 boop. Nice. Oh, that's I like. Now I have phone. So to use this segment tree, you need to implement a few things. So first you need to apply. So you apply modifier to this item. Yeah. So what does it mean? I have segment with, okay, in my case, I have sum equals to item. So this is my sum, and I change it by this modifier. Yes, you need to recalculate what will be the new sum. No, new sum will be like this. It will be a plus modifier multiplied by the length. Okay, that's it. Now here you combine two modifiers. So you make plus a and then plus b. It is the same as make plus a plus b. And finally, here we have operation. Operation is just what you calculate as a result of your segment tree. In my case, I just return a plus b. So that's it. So that's what you implement. That's what you need to implement in order to use this segment tree. Nice. Now I'll just use it. So this code I just don't read. So this is normal segment tree code. I just keep it. Yeah. And now let's solve the problem. So I take number n, make segment tree of size n. Yeah. So I don't have more than n elements in this. And my current size, so m will be 0. Not 0. I have, okay. So I have initially have 1 0. Yeah. So that's of size n plus 1 to n 1. Yeah? Now I l minus minus I do. So I read the type. If type equals 1, I need to read what a and x, and increase the first elements. So it's a modify. So I increase elements on segment from 0 to a by x. Ta-da! If t equals 2, then what I need to do? I append kickers. Okay, append. I need to set. I don't have set. I have only increase. Okay, let's say I have zeros in the end. So okay. Okay. So okay, let's take the current value. Calculate from m to m plus 1. So this is the current last element. Yes. I will modify it, this one element, because I don't want to. I don't want to change segment tree, so I will just use it as it is. Yes. By k minus x. Yeah. So now it's equal to k. And that's it, m plus plus. Now, if it is free, then I need to just m minus 1. That's it. Now I will calculate the sum of all elements. It will be calculate from 0 to m. It's my sum, and output is divided by m. Yeah. Yeah, something like this should work, I believe. It will be fun if it doesn't work. Yeah. What? So I give it my length, not the length of this. Here, actually, here divide by. I need to fix it in my template actually. Nice. So they found bug in my template code. I don't use it that often. Actually, especially this part when I recalculate using this length. But yeah. So that's it. So this is the whole interesting code. You know. So if you have some good data structure in your library, you can just reuse it and solve problem easily, much easier than I did. So again, no, again, I didn't. Sorry, it's been like 10 minutes implementing this, so it's not that important. What's important? So again, okay, let's go to how I solve this problem. I solve this problem using specific data structure specifically for this problem. So what I did instead, I solve it using some stacks with prefix sums. Because what we have actually in this problem is a stack, so we can put element in the end of the sequence, remove the last element from the sequence, and we need to add to some prefix of this sequence. And you can do it using prefix sums. Yeah. So I will maintain so this array A says, so each element of this array tells me that I need to add this number to this prefix of the sequence. Yeah. And I just carefully recalculate the sum of my sequence. Okay, so okay, let's speed up a little because I spent too much time discussing this problem. So and I make a few mistakes. So let's go to the final solution. Can you show me the final solution, please? No. Okay, let's look at it here. So that's it. So that's it. Again, it's pretty short. Yeah. But the data structure is kind of more intellectual. So you have stack with prefix sums. It's actually kind of intellectual data structure. So you need to carefully implement it. Don't make any mistakes, and it may not work. So it works in this problem. But if you are not sure if you need special structure, but you're pretty sure you can use standard segment tree, it will work. Use standard data structure. usually it's much more preferable to use standard data structure than just invent some new bicycle. But again, okay, let's go. Let's go to problem F. We spent too much time discussing problem E. Let's go to problem F. In problem F, you create some potions, and you can spend some mana to make it easier. Yeah. So initially you need to create n potions, and each potion. Okay, the main difficulty of this problem is it has too many variables input. So you input number of potions, this number of seconds. Then you have m potions, m spells like this, k spells like this. Every spell has 2 parameters. Just too many things happen at the same time. But if you read it multiple times, you probably figure out what will happen. It's not that hard, actually. So what we have, we need to create n potions. And normally, every potion can be created in x seconds. So if you do nothing, you spend n multiplied by x seconds to make all the potions. But you can speed up this process by using spells of 2 types. Spells of the first type, they decrease this number x. I thought it decreased for only one potion, but it decreased for all potions. So spell of first type basically decrease this x to some specific number a. And every spell costs some amount of mana. Spells of second time just create instantly some number of potions, so you don't need to create them now. Yeah. So basically, you decrease number of potions you need to create, and that's it. So basically, you have 2 parameters, n and x. Yeah. First spell decrease parameter x. Second spell decrease parameter n. Yeah. And you want to minimize the product of n multiplied by x. That's what's happening here. Yeah. Now, what you need to do, you have some amount of mana points. You need to make at most 1 spell of this type, at most 1 spell of this type. Basically, you choose 1 spell here, 1 spell here, activate both spells, and calculate what's on. And we will do it using 2 pointers. It's pretty standard technique. So we have some number of mana points, and we need to split this amount of mana points into 2 groups. Some mana points we'll spend on the first spell, some mana points we'll spend on the second spell. Yeah. So we'll choose one of the spells here, one of the spells here. So the total amount of mana we need is not greater than what? We have some parameter amount of mana points. S. Yeah, so parameter S, I don't hear. Well, S here. Too many parameters. Yeah, so pretty standard 2-pointer method. So strange thing is the problem that the second spells are already sorted, but the first type are not sorted. So I'm not sure why. What was the idea of the authors? I don't know. I would just sort the first spells as well. So I just sort all the spells by the amount of mana I need. Yeah. Now I just have just 2 sorted arrays. So I will sort. So I sort first spells by this number b. So number b is amount of mana I need. Yes. And second spells are already sorted by parameter d. Yeah. And now I just need to pick 2 elements here. So I and let's say j. The bi plus dj is not greater than s. Yeah. And then I can use any prefix here, calculate prefix minimums, and that's it. So that's how I usually implement 2-pointers method. You'll see. So I have special lecture about 2-pointers method, so you can go there and check it. So I implement 2-pointers method using 2 loops. So I have 1 loop by parameter j, another loop by parameter. So I move one of the parameters using for loop, simple for loop. Yeah. And I use another while loop to move the second parameter. Yeah. That's how I implement 2-pointers method. There are different implementation. That's just one which I prefer. Yeah. So I move this parameter j, this second pointer, yeah, and move this. I move this j from right to left, yeah. So this j moved from right to left, and this I will move from left to right. And I will, when I move this right, I will calculate the minimum on this prefix. Yeah, see, this a is minimum on this prefix. Well, here I understand problem incorrectly. Yeah. So I thought I can only decrease time of the single spell. So I do all spells except one in time x, and then one spell in time a. I will change it later. And then in the end, I need to check if I don't use spell at all. Yeah. So if I don't use a spell, then my time will still be x. So I get separate case. You can avoid this special case by adding special spell with cost 0. But I just add another check in the end. Okay, here I finally read the problem statement. Okay, so this is each state or each potion. I thought it's for one potion, but for each potion. Yeah. So here luckily it didn't change the solution that much. Yeah. So here you just here how you calculate the total cost like this. Yeah, and now you can eliminate one special case. Yeah. So that's it. So basic two-pointer method. Just you want to minimize function when you split your parameter in two groups, and you just basically try to a point when where you split your mana into two groups, and you use this part of mana here, this part of mana there, and just count minimal amount you can get here, minimal amount you can get here, and multiply. Get minimum out of all these possible splits. So idea is pretty simple, but again, implementation may be different. Let's look at your implementation actually. Oh, what is it? Is it divide and conquer? No, no, it doesn't look so. I don't see any recursions. So why do you have this solve? Yes, these two pointers. Okay, I'm not sure why you have these parameters. Okay, it would be fun to have some divide and conquer here. No, it's normal two pointers with multisets. Why? To maintain minimums? Because you remove. Okay, you can add elements instead of removing. That doesn't matter. Let's move next. We have two problems left. Problem G is actually a fun problem. Again, I'm pretty sure it can be solved using some specific heuristics for this problem. So again, problems like this, you have sequence of digits. You need to erase some of the digits, so the resulting number is divisible by 3. Numbers divisible by 3 if sum of digits is divisible by 3. It means you need to remove at most 2 digits. And the tricky part is that you also have zeros, and you need the final number be without leading zeros. That's maybe the tricky part. So if not this part, you can just so you look at the remainder modulo 3. If it's equal to 0, you're already done. If it's equal to 1, you need to remove 1 digit with remainder 1 or 2 digits with remainder 2. Or if the remainder is 2, you need to remove 1 digit with remainder 2 or 2 digits with remainder 1. Something like this. So I believe you can solve it just by track all these special cases, and I mean not that many cases. But I thought it's not fun to mess with all these cases and get possible wrong answer test number 25. Okay, so instead of this, I will just use dynamic programming because I thought it will be less painful, let's say. So for me, when I see I can solve problem using dynamic programming, I would normally do it. Dynamic programming is one of the most, let's say, stable ways to solve the problems. Not that many things can go wrong in this thing. So if your idea is okay, then dynamic programming will find the so. So if you see how the optimal solution is constructed, dynamic programming will find the optimal solution. Yeah. If you're not sure how the optimal solution looks like, then it's more fun. Then probably your dynamic program will not work. But if you're pretty sure how the answer looks like, yeah, then the dynamic program will just find you the best answer. What I'm doing here, I'm doing dynamic programming. Dynamic programming by two parameters. Just very standard dynamic program actually. So I go from left to right and pick some digits and remember the current remainder modulo 3. Yeah. So my dynamic so I have this array of dynamic programming. I have the prefix I have and the current remainder modulo 3. Yeah. So I have array like n by 3. So I go from left to right, take the element and look at the next digit, and I either skip it or take it. So if I skip it, I go to state I plus 1j. Okay, here I thought I need to reconstruct the answer, so I need to remember this backwards pointer. So I remember how I get this answer. You see. And if I take the digit, I calculate the new remainder modulo 3. It's just my current remainder plus this digit modulo 3. And again, try to make this step. So I usually make the improvement forward. So I take my current state and make one step forward and update the next state. It's one way to do it. Yeah, that's it. So here I'll check update. That's it. That's normal dynamic programming. Yes. So this if, okay. So this if is here to prevent leading zeros. So I don't put digit 0 if I don't have digits. So dij is number of digits I already have. If it is equal to 0 and my current digit is 0, I just don't take it. Yeah. So this is how I prevent leading zeros. Also, if you may, so you can see that here 1 0 is actually allowed. So number 0 is different. It kind of has leading 0. Yeah. So I just solve this problem separately in the end. So here I just check that my numbers are okay. Yeah. So this length is okay. So d and 0 is just the length of the number. Number of digits I can have. Yeah. Now I just need to restore the answer. So yes, I track separately this case when I have equals 0. So I can take one digit equal to 0 if I have one. If I don't have one, I just output -1. Okay, now if not, I just use very standard operation of restoring answer in dynamic programming. So I go from right to left and restore my answer. Very standard. Just skip this. Yes, and I have it in reversed order, so I reversed in the end and just output it. That's it. So again, you may create some very specific solution for this problem. I believe it's possible to just track separate cases, and there will be not that many of them. Or you can use very standard dynamic programming. In this situation, I would normally prefer use standard dynamic programming. Yeah. Again, it's just about consistency. It's just more consistent way to solve the problem. Yeah. So if I try to invent something strange, with big probability I will have some strange mistakes in the middle, and I will just miss some cases, or I will track them wrong and do something do some mistakes which I don't want to make. If I solve it using dynamic programming, I'm pretty sure I can do it without any big mistakes. Yeah, because I wrote code like this like thousands of times. Yeah, so dynamic programming is very standard technique. If you did master dynamic programming by now, just solve more problems by dynamic programming. Very useful. Yeah, and it's very useful, and it's very standard. Once you understand what's going on here, you can just write code like this without many thinking. Yeah. Okay, last problem. In the last problem, so you need also, okay, if you didn't read it, so first why go read it. So what you need to do is to find so in a given sequence of so given some bracket sequence, you need to find a number of substrings which are correct bracket sequences. Okay, so I'll skip the first part. In the first part, I misread the stems. I just thought you need to count number of substrings as like, so number of ways to cut a bracket sequence. That's my mistake. I'm not sure why I missed this. Maybe I was too tired by this point. It does work on the first example. So I thought, okay, so I thought if you have different occurrences of the same record sequence, you count them multiple times. It's definitely not. It's just written here. You don't. It's just in the first example it does work. But then I implemented it wrong and I made mistake. So I misunderstood the problem statement and then make mistake in the code. So it magically pass all the example tests and fail only in test 5. Okay. So and then I fixed my mistake and now it doesn't pass even the first test. So now finally I'm thinking. Okay, and here I find why the first answer for the first example is 5. That's okay. So normally in a normal contest, I would go here, read the first examples, try to solve them by hand, and then just to check if my understanding of the problem statement is correct. Here I didn't do it. That's my mistake. Okay, so try to first understand your problem. Make sure you understand the problem correctly. If you don't, then you will solve the different problem. It will not help, like here. So I spent a lot of time just solving the wrong problem. Don't do it. Now the correct problem is actually to calculate number of occurrences, or again, number of different correct bracket sequences which occurs in your string. Okay, here I will spend some time just convincing myself I can do it without suffix structures. But I obviously cannot. No, why? No, because this problem is not easier than just counting number of different substrings. So it's just string problem. So this property that I count different substrings. So it's basically, so if you have just string constructed of, like, again, let me show you. So if you have string which have some a or something like this, and then like this, and then something like this, yeah. So you make string only on 2 blocks, block like this and block like this. So if you replace an a's and b's, yeah, then basically you have string of a's and b's, and you need to count number of different substrings. Yeah. So this problem is not easier than counting number of different substrings. And for this problem, you need some kind of suffix data structure, some suffix array, suffix tree, something, suffix automaton, something like that. So you need some suffix data structure. And I spent some time trying to convince myself I can do it without suffix structure. Okay, at this point, I think, okay, I need some suffix data structure. So I chose to use suffix arrays because I like suffix arrays. Now, even if you convince yourself you can use you need to do suffix structure, it's not stops there. You need to solve now you actually need to solve your problem. Now you think, but now you have some, okay, okay. Now you know that you need data structure. You need some specific data structure, some suffix data structure. So you think, okay, imagine I have suffix data structure like suffix array. How my problem looks in terms of this data structure. Yeah. So what normally happens? So again, this problem looks similar to problem of finding number of different substrings. Yeah. So I think how I solve problem of finding number of different substrings. Now I do it like this. I make suffix array, calculate LCPs of consecutive elements, yeah? And then number of new substrings will be length of this substring minus LCP of the previous one, yeah? So here, okay, so here. So you take substring, take the previous one. So all these prefixes except this will be new, yeah? So number of new strings will be length of this suffix minus LCP, yeah? Okay. Here I tried to find the good implementation of LCP. Okay, now I copied my suffix array from my library because I can. Up. So this is my implementation of the suffix array. Again, I have a full. Okay, so here is my implementation of the suffix array. Again, I have a full lesson about suffix arrays on Codeforces, so you're gonna go check. Here, I don't remember how I used it before, so I didn't use it that often. So here I just check what's happening. So if I give it some string, what will happen? Yeah. So here I see something strange happens. So it doesn't look very sorted. See, they should be sorted. So I spent some time thinking, but yeah. So my implementation thinks that I have special characters in the end of the string. That's how you usually implement suffix array. No? Okay, some implementations, okay, it probably would be better to add this special character inside the constructor of this data structure. I didn't. So that's it. So I take this string. These are all suffixes in sorted order. Yeah? My suffix array create this suffix array plus array of LTPs using Kasai and others algorithm. Yeah. So go. Okay. So now I actually solve the problem. So how did I solve the problem now? Let's see. So what's happening? So you take the suffix. Yeah. What I want to do, I want to find some prefixes of this suffix which are correct bracket sequences. How it looks like. So I have some. So it only can happen if the first character is opening string. So if I have opening bracket here, then I have something, then I have correct bracket sequence. Yeah. I may have more characters, so I may have another opening bracket, something, and then another bracket sequence like this. Yeah. Then I have this prefix and this prefix, and then something else. Yeah. Yeah. So again, in my suffix array, I have suffixes. Every substring is prefix of the suffix. So I take this suffix and count prefixes of this suffix, which are correct bracket sequences. Yeah. So I may have several correct bracket sequences if I have situation like this. So here I have open bracket, here I have corresponding closing bracket. Inside I have some correct bracket sequence. Yeah. And here again I have closing bracket and again opening bracket, and inside I have correct bracket sequences. Yeah. So what I need to do, I need to count this number of times I can do this. Also, I need to skip. So I have previous suffix. Yeah. In this suffix, I have some common prefix. So this prefix is the same. Yeah. If this prefix is the same, means this string is already calculated. Yeah. So I need to skip all the prefixes which already calculated before, and now calculate all prefixes starting from this point, which are good correct bracket sequences. Okay, hope it was clear enough. How I do it? I do it like this. I pre-calculate for each for each opening bracket, I find the corresponding closing bracket if it exists. So here I have some correct bracket sequence. Yeah. And then from here I make pointer here. Yeah. Here again I have correct bracket sequence. I'm like pointer here. Yeah. So these pointers will allow me to jump to the next to the next bracket after my correct bracket sequence finishes. Yeah. And so the answer will be like this. I need to jump from here. So now I have these jumps. I have this already calculated prefix. I need to make these jumps until I get out of this prefix. Yeah. And starting from here, every jump is a new good sequence. So I need to count this point, count this point, count this point, count this point. Yeah. So I need to make these jumps until I get out of this prefix and then count number of jumps I can make from here. Okay, hope it's clear enough. Now, this problem is, again, pretty standard. You can do it using binary climbing. So I will pre-calculate binary climbings, and I will just go from here. You need to make as small number of jumps as possible to get out of this prefix. Yeah, you can do it using binary climbing technique. And then starting from here, I need to calculate number of jumps I can do. I can pre-calculate it. So for every position, I will pre-calculate number of jumps I can do, and then make binary climbing over that. Okay, you will see. Okay, just to make it more clear what I will do next. Right now, what I'm doing, I'm just playing with my suffix structures, and now I will calculate these jumps. Okay, so here. So I go from right to left. Yeah. For every closing bracket, I remember the balance. So I remember balance of the closing bracket to find the corresponding bracket for opening brackets. So if you have opening bracket, the corresponding closing bracket is the bracket with the same balance. Okay, I believe I could do it using stacks. Doesn't matter. So it's the closest bracket with the same balance. So I remember the closing bracket with the same balance. So now when I have opening bracket, I see if I had closing brackets with the same balance, it means I have this correct bracket subsequence, substring. Yeah. Okay, spend too much time. Okay, here I make binary jumps. Here I calculate jump. So I will jump to the next bracket after the closing bracket. So I have this opening bracket in position I, closing bracket in position J. So I make jump to position J plus 1. Yes, and also I need to calculate number of jumps I can do. Yeah. So this is the final code. Spend some time to figure out how to do it easily. That's how we do it. Yeah. So this NM is number of jumps I can do from this point. Number of these correct bracket sequences from this part. Here I just check that I calculate all the numbers correctly. Yeah, looks okay. So what I'm doing now, I calculate binary climbs like normally do. So this is very standard. So I just calculate binary climbs like I normally do. Yeah, here. So what I'm doing here, I wanna skip all the sequences which already calculate all the bracket. Yeah. I'm just thinking, can I do it easily or not? I don't know how to do it easily. We'll check your solutions later, but okay. So again, yes, so I make this. So here. So here I make these binary jumps. Yes, you see. Okay, I made mistake here. So here I'm trying to stay inside. I need to actually go outside. So I need to make one more jump. Yes. So if I have something, I add this +1 to the result. Okay, here I debug it a little. Skip. Show me the final part, please. Oh. Okay, I'll just show you the code here. No, not this. So this is just suffix array. Nothing interesting here. Suffix array plus LCP. So this is the intellectual part. So here I'm calculating for each opening bracket the next bracket after it will close. Yeah. So here, and also I calculate number of jumps I can do. Here I make suffix array for each element. I take x is the position. Yeah. So p is just suffix array. Yeah. So I take the position of the suffix. Check if it starts from opening bracket. Maybe I don't need this, so I just break. Here I find LCP with previous. Now I try to skip all elements I already calculated using this binary claimings. Then make one more jump. So now I'm out of this prefix. So yeah, here I make binary jumps until when I trying to stay inside this prefix. Yeah. And so this is the first position outside of the prefix which I need. Yeah. I check if it exists. Then I add this number of jumps to my result. No, plus one because how it's calculated. So I calculate this plus number of jumps. Yeah. That's it. That's it. Very complicated code. So let's check your solution. I'm very curious. Maybe you have something easier than me because you solved it so fast. Let's check. Okay, this suffix array. That's also suffix array, I believe. Okay, it's too much code for suffix array. But where? Okay, so okay, so this is my code. Do you have you use a coder library? Oh, why not? Okay. Do you use you don't use binaries, you use upper bounds instead. It actually makes a lot of sense. So you have these sequences of correct bracket sequences. And you just put them in these arrays. Now you don't need binary claiming. You just in this so in these positions, you just find the first position out of your prefix. Yeah, maybe this is easier than mine. No, not that much, but yeah. Yeah, just keep all elements with the same balance. And here, yes, you need to remove an invalid sequence. So if you go below this balance, you need to so all the elements to the right are just wrong because okay, makes sense. So again, the idea is to split all the position. Okay, let me show you. So if you start at some position of your sequence, and you from here you want to find the correct bracket sequences. So you start from here, you go somewhere, then you go back. So you go up when you have open, when you have down, you have close bracket. Yeah. So this is my balance. Yeah. Yeah. So for every element, you can find the next element with the same balance. If you don't have below, if you go below, then you have some element before. Yeah. So if you start here and then you have before, then you have to, then from here you will go here. Yeah. And now all these positions will be kind of split into sequences. So from sequence from here to here, Then you have again, they have pass from here to here and so on. So instead of making these jumps, you just put them in these lists because they form a list. Yes, I think if you look at my program and you look at these jumps, yes, just yeah. Yeah, the idea is this they don't form a tree, they just form number of lists. So you can do it using normal binary search and without this binary. Yeah. Actually makes a lot of sense. Yes, it makes a lot of sense. Good for you, good for you. How to solve that fast? Okay. Very impressive, very impressive. So that's it for today. See you next week. Next week we'll have the final contest. So I decided we'll have contest 25 and then we will finish this season. So see you next week for the final discussion.